Hello friends, so today we are going to start do the questions from rotational motion. And these questions are from the year 2024. We are going to solve total 10 questions, and all these 10 questions are from the mains only. And for the year 2024, this is part 1. There are some questions remaining from the mains and also from the advanced version of this 2024, which we are going to try to cover in part 2, or if required we will also do a part 3 for the year 2024. So the first question: a solid sphere and a hollow sphere roll up without slipping on same inclined plane with same initial speed v. The sphere and the cylinder reach up to a maximum heights h1 and h2 respectively above the initial level. The ratio of h1 and h2 is n by 10. The value of n is. So in this case, we are given that they are rolling up the inclined plane, and from that we are going to find out their respective heights are h1 and h2. We have to find out the ratio of h1 and h2. So in this case, it is saying that it is rolling without slipping. Okay. So from here you can say that total kinetic energy at the start and the motion is rolling without slipping. Rolling without slipping. So therefore we can write total energy K is equal to our half m v square plus half I omega square. And we can write that our omega is equal to v upon r, and our I will be equal to km multiplied by r square. So if we substitute both these values, we get, okay, one second, let me write this kinetic energy as Ke. And therefore we can write that our kinetic energy will be equal to, this will be our half m v square plus half, and in place of I we can write as km r square, and omega is our v upon r, and this comes as whole square. Therefore our kinetic energy will be equal to half m v square, and this comes as 1 plus k. Now they respectively reach at a height of h1 and h2. Therefore from the conservation we can say that all the kinetic energy is converted into the potential energy. So we can say at maximum height kinetic energy is equal to our potential energy. Therefore we can write that our mgh will be equal to half m v square 1 plus k, and here this m and m cancels out. Therefore, because we are only interested in height, because ratio is to be found that is in the height, so we can say h is equal to v square 2g 1 plus k. Now we have two different objects, one is solid sphere, other one is a hollow sphere. So we can say for solid sphere, and for the solid sphere we know that value of I, that is moment of inertia, is equal to 2 by 5 mr square. Therefore value of k is equal to 2 by 5, and for the respective height in that case is our h1. So we can say our h1 is equal to v square 2g and 1 plus 2 upon 5, and this comes as 7 upon 5 v square upon 2g. And next object is our hollow cylinder. Hollow cylinder, and in that case the moment of inertia is given as mr square, and therefore value of k is equal to 1, and height for hollow cylinder is given to us as h2. So we can write our h2 is equal to v square upon 2g 1 plus 1, which comes as 2 v square upon 2g. Now we just can find out the ratio. So we can say our ratio, which is h1 upon h2, will be equal to 7 upon 5 v square upon 2g 2 v square upon 2g. This v square 2g cancels out, and we get this as 7 upon 5 and multiply by 1 by 2, which gives us 7 upon 10, and this is given to us as n upon 10. So we have this as n upon 10. Therefore we can say that the value of n is equal to 7. So value of n is 7. Next question. It states that ratio of radius of gyration of a hollow sphere to that of a solid cylinder of equal mass for moment of inertia about their diameter axis AB as shown in figure is square root of 8 upon x. The value of x is. So we are given the radius of gyration for our cylinder and hollow sphere as well as cylinder, okay, with respect to the diameter. And so we have two objects. So let us start with the hollow sphere. So for hollow sphere we can write that 2 upon 5 mr square will be equal to mk1 square. Therefore our this m and m cancels out, and we get that our k1 will be equal to r, sorry, it is 2 by 3, not 2 by 5, 2 by 3, and this comes as our r square root of 2 by 3. Similarly, we can write for solid cylinder, and you can say that for solid cylinder, and the solid cylinder, the radius axis on which it is radius of gyration is to be found out is along one of its diameter. Diameter is 2r and the total length of the cylinder is 4r. Therefore, we can write that our diameter is our 2r, therefore its radius will be equal to r, and so we can say that our mr square by 4 plus we have this as m by 3, and the distance is our 4r whole square. This will be equal to our m k2 square, and here also this m cancels throughout, and we get this as r square, and we get this as r square by 4 and 16 upon 3 r square. So from here we can say that our k2 square will be equal to r square, we can take as common, we are left with 1 upon 4 plus 16 upon 3. Therefore, our k2 will be equal to r square root of 67 upon 12, and we have to find out the ratio. Okay, therefore ratio is our k1 upon k2 will be equal to k1 is our r square root of 2 by 3 and k2 is our r 67 upon 12. Here r and r cancels out, and this can be written as 2 by 3 multiplied by 67, and this comes as 12 and its square root, and 12 goes by 4, so this will be equal to 8 by 67 and its square root, and it is given as 8 by x, so we can just equate it. We got 8 upon 67 divide and 8 upon x, therefore we get our x is equal to 67. So option 3 is correct. Is correct. Next question. It states that a hollow sphere is rolling on a plane surface about its axis of symmetry. The ratio of rotational kinetic energy to its total kinetic energy is x by 5. The value of x is. So here we have to find out the ratio of rotational kinetic energy and total kinetic energy. And obviously it is rolling, so it should be doing it rolling without slipping. Okay. So first of all, about its axis of symmetry, let us say that it is moment of inertia. Moment of inertia of hollow sphere about diameter. that is I will be equal to 2 by 3 mr square. And for rolling motion, we know that for rolling our V is equal to R omega. Now we have to find out the rotational kinetic energy. So we can say our rotational kinetic energy let us call this as kr, and one second, yeah, kr, and that will be equal to over half I omega square. We can substitute value of I, that is our 2 by 3 mr square, and we can also substitute our omega, and omega will be equal to our, let me write this, omega is equal to V upon R. So this comes as V upon R whole square. Therefore our rotational kinetic energy, that is kr, will be equal to this 2 and 2 cancels out, and r square and this r square will be going away, so we are left with half mv square, half mv square. And the second energy that will be associated with it will be called as a translational kinetic energy. So you can say translational kinetic energy, let us call this as kT, and that will be equal to over half mv square. And the total kinetic energy, let us call that a K, that will be equal to rotational plus translational, and it has to be 1 by 3, and this will be coming as mv square, we can take as common. Inside we are left with 1 by 3 plus 1 by 2. So we get our total kinetic energy is K, that will be 6 and 5 by 6 mv square. And we have to find out the ratio between the rotational and total kinetic energy. So we can say our ratio is K rotational and total, and rotational is our 1 by 3 mv square, and total is our 5 by 6 mv square. mv square cancels out, and this comes as 1 by 3 multiplied by 6 by 5, and this 6 goes by 2, which is our 2 upon 5, and this is given as equal to x upon 5. Therefore value of x is equal to 2. So value of x is 2. Next question, it states that if the radius of Earth is reduced to 3/4 of its present value without change in mass, then the value of duration of the day of the Earth will be dash hours and 30 minutes. Okay. So in this case, we are going to use that product of angular momentum, angular velocity and moment of inertia is constant. Okay, and we can just write that I omega is our constant, and which basically means that at I1 omega 1 is equal to I2 omega 2, and it is given that and because it is it says that there is no change in mass, and same shape is to be maintained, only the radius is 3/4, and we know that our moment of inertia is proportional to our r square, because it says that same mass. And therefore we can write that our omega 2 is equal to I1 I2 multiplied by omega 1, and I1 is suppose having a radius of r1 and I2 is proportional to our r2 whole and omega 1, and it is says that it is 3/4. It means the ratio of this r1 and r2 will be our 3/4, so this comes as 3/4 whole square and omega 1, which will be coming as 16/9 times omega 1, and we have to find out how the duration of day is going to change. And let us suppose the time duration is represented as t2, so we can say that our t2 will be equal to 2 pi upon omega 2, and omega 2 we know is our 16/9, so this comes as our this comes as our 2 pi, and we have this as 16/9 times omega 1, which can be written as 9/16 and 2 pi upon omega 1, and this factor is nothing but our t1, so we can write this as 9/16 times t1, and value of t1 will be equal to our 24. Therefore we can say our t2 will be equal to 9/16 multiplied by 24, which gives us 13 hour and 30 minutes. Therefore we get this as 13 hour and 30 minutes. Next question. It states that 3 balls of mass is 2 kg, 4 kg and 6 kg respectively are arranged at the center edges of equilateral triangle of side 2 meter. The moment of inertia of the system about an axis through the centroid and perpendicular to the plane of triangle will be dash kg meter square. So we have to find out the moment of inertia about the axis which passes through the centroid and is perpendicular to the plane of the triangle. So first of all, let us draw the approximate figure. So we are having a equilateral triangle, and the masses are given at the center of the edges. So let us suppose this is our 2 kg and this is our 4 kg, and here we are having 6 kg. Okay, and let us join them. And the centroid, suppose this is our centroid, and the axis will be perpendicular to the plane of the paper. It means it will be something like vertical. Okay, and side of the equilateral triangle is given as 2 meter. Therefore, let me join the centroid. So if we join this centroid, and let us call this distance our r, and all the side, it is equilateral triangle, therefore the internal sides will be also over 1 meter each. So let us assume that the side of the equilateral triangle is represented as A. So you can say that side of a triangle, let us suppose that is A, which is given as to us as 2 meter. Therefore height h will be equal to square root of 3 divided by 2 and multiply by A. So from here we get that our h will be equal to 3 by 2 multiplied by 2, giving us that the h is equal to square root of 3. Okay. And the distance of the centroid to the midpoint of its side, okay, which we are here calling as r. So we can say that distance from centroid to the midpoint of a side, midpoint of a side, in this case that is our r, will be equal to h by 3. H is our root 3, so this comes as a root 3 divided by 3. And we have to find out the moment of inertia through the centroid. Let us call this as O. Okay, centroid is our O. Therefore, total moment of inertia, total moment of inertia, in this case we can use the general formula for moment of inertia, which gives us summation of all the masses and the distance square. Okay. And here we are having 3 masses, so value of I will be our 1, 2 and 3. So value of r is same in this all the cases, that's why we have written only r. Otherwise we can just make certain adjustment in this distance formula, this distance also. And so we can write this will be equal to over m1 plus m2 plus m3, and this comes as our r square, and this comes as 2 plus 4 plus 6, and our r square is our 3 by 9. So we get this as 12 multiplied by 3 by 9, and this 9 goes by 3 and 12 goes by 4. So therefore we get this moment of inertia will be equal to 4 kg per meter square, 4 kg meter square per meter square. I think it should be per, I'm not sure. Meter square, because here it is meter square. Next question. states that a thin circular disk of mass m and radius r is rotating in a horizontal plane about an axis passing through its center and perpendicular to this plane with angular velocity omega. If another disk of same dimension but of mass m by 2 is placed gently on the first disk coaxially, then new angular velocity of the system is. So in this case we are given that so we can divide this entirely into two parts. Let me draw two figures, approximate one. So we have a thin disk and whose mass is given as whose mass is our capital M, and it is rotating about the axis which is passing through the center, and the radius is given as our capital R. So this is its radius and it is rotating, suppose, in this direction, and value of angular velocity is said to be over omega. In the second part, we place on the top of this same dimension but mass is m by 2. Okay. So let me draw, this is our original disk, and on the top of it same dimension is placed, and their axis of rotation is same. Here the radius, because it is same dimension, so radius will be r, but the mass is our m by 2. So mass of the disk is our m by 2 and original mass is our m, and it is rotating in this direction. Okay. So the general formula we already know, that let us suppose the moment of inertia in the first case is I1, in second case is it I2. And we can say that moment of inertia in the first case that is of I1 is equal to 1 by 2 mr square, and moment of inertia of the second disk, moment of inertia in second case, one second, let me rephrase it. Let me write it that our first disk so in first disk you can write that its moment of inertia will be equal to I1, which is our half m r square, and for second disk the moment of inertia is our I2, which is equal to half mass is our m by 2, and we have this as r square. So we have, okay, so let us find out the initial angular momentum. Initial means only having one disk, so this is our initial and this is our final. Final is having two disks and initial is having only one disk. Okay, so we can see initial angular momentum let us call this as Li, which will be equal to I1 omega, and we can write that our Li will be equal to I1, we already know, is our half mr square. So this comes as half mr square times omega. And okay, and now we can find out the final moment of inertia. Final moment of inertia, let us call this as IF, will be equal to moment of inertia because of the first disk plus moment of inertia of the second disk, and that will be equal to our half mr square plus 1/4 mr square. So we get our moment of inertia final will be equal to, this comes as 3/4 mr square. Therefore, let us assume that the angular velocity is our omega f. So we can find out our final angular momentum. Final angular momentum, let us call this as LF, will be equal to our final moment of inertia multiplied by angular velocity. Therefore, we get that our LF will be equal to IF is our 3/4 mr square and multiplied by omega f. Now we can use conservation of angular momentum. Conservation of angular momentum, we can write that our initial angular momentum is equal to final angular momentum. So we get this as our 1/2 mr square times omega is equal to 3/4 mr square times omega f. And mr square goes away, this 4 goes by 2. Therefore, we get that our final angular velocity is equal to, this comes as 2/3 omega. So we get this as 2/3 omega. Option number 3 is correct. Next question. It states that a block is simply released from the top of inclined plane as shown in the figure above. The maximum compression in the spring when the block hits the spring is. So basic figure is given to us. We have inclined plane at an angle of 30 degree and box is placed at the inclined length of 10 meters. And there is this inclined plane is frictionless, and just at the end of inclined plane we are having a frictional distance of 2 meter with coefficient of friction 0.5, and then we are having a spring whose constant is given, a spring constant is 100 Newton per meter. We have to find out the compression, that is value of x by which it is compressed. So this is directly based on the conservation of energy. So we can say energy conservation we can write that loss of mechanical energy loss of mechanical energy will be equal to spring plus work done against friction. Work done against friction. Or in the simpler terms, we can write that all these sum will be equal to 0 with the respective signs. And therefore, in terms of equation, we can write this as mgh minus our force because of the friction, and we are having that x minus half k x square is equal to 0. So let us substitute the values. We get this as 5 into 10 into 5 minus the coefficient of friction is 0.5 multiply by weight is 5 kg and the distance is our 1 second. So let me rephrase this again, because so first of all, let's find out what will be the height of this. Otherwise it will be, suppose h is the height, therefore we can say that the height of the block, which is our h, is equal to 10 sine of 30, and this will be coming as 5 meters. So based on this, we can easily find out its potential energy at the top. So we can say potential energy at the top, this will be equal to our mgh, and mass is our 5 kg, g is 9.8, and height is our 5 meters. So we get this potential energy will be equal to 245.25 joules. And let us suppose that v is the velocity when the block reaches the spring. So here the velocity is v. Therefore we can say the kinetic energy of the block can say kinetic energy when the block reaches the spring. And that will be equal to our kinetic energy is equal to our half m v square. And according to the conservation of energy, we can write that conservation of energy, we can say that the potential energy at the top will be equal to kinetic energy just before it is going to compress the spring. Therefore we can say that our half mv square will be equal to this, we got at 245.25. This gives us that our v square will be equal to 2 multiplied by 245.25, mass is our 5. Therefore the velocity will be approximately equal to 9.9 meter per second. And this our So let us assume that the spring is compressed by a distance of x. So it means the kinetic energy is converted into, because of the compression, elastic potential energy. So we can say when the spring is compressed, when the spring is compressed, suppose that is our x, Therefore, we can write that our half kx square will be equal to our kinetic energy, and that kinetic energy is about 245.25. So from here we can say that our x will be equal to 2 times 245.25, and value of k spring constant is given as 100. So we get, this is our x square. So we get our x is approximately equal to 2 meters. Okay. So it is option number 2 is correct. Two is correct. Next question. It states that a heavy iron bar of weight W is having one end on the ground and other end on the shoulder of a person. The bar makes an angle theta with the horizontal. The weight experienced by the person is. So in this case, let us first of all draw an approximate figure, and we are given a bar which is making an angle of theta with the horizontal. Suppose this is angle of theta, and this is the shoulder of the person. Okay. And there will be a weight in the downward direction, that will be over mg, and here we are going to have a normal reaction. Let us suppose we call this as n1, and here let us call this as our n2. Okay. And we can just make use of our, you can say, because it says that the rod is balanced, so let us call this as point as A, this point as C, and this point as B. So as the bar is in equilibrium, bar is in equilibrium, we can balance it with respect to the moments about point A. Balance moments about point A. So let us assume that the length of the bar is capital L. Okay. Therefore, point C, because mg will be acting exactly at the center, so this point C will be at a distance of L by 2, and let us, this horizontal distance will be our L by 2 cos of theta, and this entire distance will be our L cos of theta. So let me mark it here. This entire distance will be our L cos of theta. Okay, up till this point will be our L cos of theta, because we are going to find out the moment about point A. So we can write that length of bar is capital L, therefore center of mass from point A will be equal to L by 2, and the horizontal distance let us call this point as our C prime and this point as our B prime. So horizontal distance AC prime will be equal to L by 2 cos of theta, and our horizontal distance AB prime will be equal to L cos of theta. So now we can just take the moment about point A. Moment about point A, because of this n1 it will be equal to 0, so we are going to have only the moment because of our n2 and because of our mg. Okay. Therefore we can write that this is our n2 multiplied by the perpendicular distance, or in this case we have written it as a horizontal distance, that is our L cos of theta will be equal to our mg, which is our, in this case it is W, so let us replace mg by W, and the horizontal distance, which is basic perpendicular distance, is our AC prime, is our L2 cos of theta, and our L2 cos theta, L and cos theta cancels out, thus we get that our N2 will be equal to W upon 2. So option number 1 is correct. One is correct. Next question. It states that a string is wrapped around the rim of a wheel of moment of inertia 0.4 kg per meter square, kg meter square, and radius 10 centimeter. The wheel is free to rotate about its axis. Initially the wheel is at rest. The string is now pulled by a force of 400 Newton. The angular velocity of the wheel after 10 seconds is x radian per second. The value of x is, and in this case okay, so we are given that we are having a rim, so let us put this here rim, and there is a string wrapped around it. Okay, so let us suppose this is a string wrapped around it, and this is the loose end of the string through which it is supposed to be pulled. Okay, and we are going to apply a force that is suppose F, which is our 40 Newton, and this is free to rotate. Okay, so it is going to rotate, suppose obviously in this direction with the angular velocity, that is our omega. Okay. And the radius of this is about 10 centimeter, and so we have a force F, and we have a, let me mark the radius from the top side. This is the center and this is our R. In this case, this will be acting as a perpendicular distance also. So this force is going to produce a torque. Okay. So we can say torque produced by force F will be equal to, suppose tau is equal to force multiplied by radius, which in this case is also perpendicular distance. Therefore, we can say our torque tau, force is given to us as 40 Newton and radius is about 10 centimeter. So this comes as 0.10, which gives us 4 Newton meter. And moment of inertia is also given to us, so we can find out the angular acceleration. So we can say angular acceleration, let us suppose that is of alpha, and alpha will be equal to torque divided by moment of inertia. Torque is a 4 and moment of inertia is given to us as 0.40. So this comes as 10 radian per second square, and it states gives us that the wheel is at rest initially. So we can say that our starting from rest, okay, which basically means that omega naught is equal to 0. So we can use the equation that omega is equal to omega naught plus alpha t. Omega naught is 0, so we get omega angular velocity is equal to alpha times t. Alpha is about 10 and time is also about 10. So this comes as 100 radian per second. Okay. So value of x is about 100. Next question. It states that a circular disc reaches from top to bottom of an inclined plane of length L. When it slips down the plane, it takes t seconds. When it rolls down the plane, it takes alpha by 2 raised power 1 by 2 t seconds. Where alpha is, okay, we have to find out the value of alpha. So we can just draw an approximate figure, and suppose this is a slant and making an angle of theta, and we are having a disc, and the acceleration, let us suppose, is given as a in the downward direction. So we are going to have our mg, and this mg can be divided into components, and this angle we have theta, so we get this as mg cos of theta, and along this we are going to get this mg sine of theta. Okay. And the length up till this point is given as L. So here we are having two motions. First is our slips and second one is our roll. Okay, and so we can write that time to slide which basically means no rotation, that is our t, and time to rotate or time to roll which means no slipping, without slipping, and that is given to us as alpha upon 2 times t, and let us call this particular in this case as tr. Later we can just substitute it. So in the sliding, the acceleration will be, let us suppose, as. So for sliding, okay, in this case we have to remember that it is only sliding motion, so there will be no frictional torque, no frictional torque. Thus we can say the acceleration, let us call this as our A of s, will be equal to g sine of theta. Okay, and our length is given as L and it starts from rest, therefore we can use the formula S is equal to ut plus half at square. So we can say that S is equal to ut plus half a t square. Excuse me please. Here S is our L, so we can say L, U is our 0, so this goes away, and so our L comes as our half acceleration. We have said that is our A of s, and t is obviously in this case also t, so this comes as t squared. So from here we can find out value of t. So we can say our t will be equal to 2 times L, and we substitute value of as, which is g sine of theta and its square root. Okay. And we come to the next, that is our rolling. So we can say for rolling, so in this case let us suppose the moment of inertia is our I. Moment of inertia is, let us suppose, our I, and radius is capital R. Radius is capital R. So it will be rolling without slipping. So there will be two types of equation involved in this rolling. One will be the translational, another will be the rotational. Okay. Therefore we can say our translational motion this translational motion, our let me draw the figure for this particular case. So it is going to roll in the downward direction. Let us suppose the velocity is, angular velocity is omega. So the torque, there will be a frictional force in the upward direction, okay, and in the downward direction is our mg sine of theta. and the acceleration, let us suppose in this case, is AR. Therefore we can write that our mass multiplied by AR will be equal to mg sine theta minus frictional force, that is our F. And next motion is our rotational motion. And for that we can write, we assume that radius is our r, so the torque will be our F frictional force multiplied by radius r. So this comes as F times r will be equal to I multiplied by our angular acceleration, that is our alpha. In this case, let us assume that is a alpha rotational, that is alpha rotational. And the relationship between the rotational acceleration and the translational acceleration, that is r, we can write this as alpha rotational will be equal to alpha r divided by capital R. So from here we can find out our frictional value, that is our F. So we can say that our F will be equal to our I alpha rotational divided by R, and we substitute it to the translational equation. Therefore we get this as ma of r is equal to mg sine of theta minus, we have this as alpha, I r, and we substitute value of our rotational and equation, and this comes as our multiply by alpha r divided by, one second, not alpha r but a of r, and divided by r. Okay, now it's we are going to just make some changes, and we can take a of r as common. So we get a of r, and we have this as 1 plus I upon mr square is equal to g sine of theta. Therefore we can say that our a of r will be equal to g sine of theta divided by 1 plus I, and we have this as mr square. Now the length traveled is same in this case also. Therefore we can say time to travel, length L, under acceleration AR, under acceleration AR. And for this particular case we have said this time is our T of R. This will be equal to 2L and square root of AR. Okay, same case as we derived previously also. And we substitute value of our AR. So we get this TR will be equal to 2L G sine of theta multiply by and 1 plus I upon mr square and its whole square. So we are going to use that our t is equal to square root of 2l g sine of theta. Okay, so it means we are going to substitute this part. So this comes as t and square root of 1 plus I upon mr square. Now we can just, you can say, find the value of alpha. Okay, we are given that t of r is given to us. This t of r is our square root of alpha upon 2 multiplied by t equal to t 1 plus I upon mr square and its square root. So here this t and t, square root and square root goes away. So we get this as our alpha upon 2 is equal to 1 plus I upon mr square, which gives that alpha is equal to 2, and we have this is 1 plus I upon mr square, and it is given as a circular disc. So we can just put the value of I, moment of inertia. So you can see for disc, the moment of inertia is our 1 by 2 mr square. Therefore we get that alpha is equal to 2 times, and we have this is 1, and we are left with this as half mi square, and okay, let me write it here also. I upon mr square is equal to 1 by 2. So this comes as 1 by 2. So this will be 2 times 3 by 2. Here 2 and 2 goes away. So we get value of alpha is our 3, which we were supposed to find out. Alpha is 3. This is, in this case I tried all the equations, but in case you know the formulas, you can just substitute and get the answer. Okay. So this completes all the 10 questions for the year 2024, and this was the part 1 for the year 2024 for rotational motion. So this completes the 10 questions. Thank you.